and so the actual formula don't matter too much for actual implementation. I learned last time that at least some people in your research group use Stata, uh, and R and SAS are a couple other common choices as well. And they'll all be consistent on answers they give to any of the analyses that I talk about. An important piece of statistical analysis is what to do with the results when we're done, and that's the interpretation piece that we'll touch on. I want to talk about how to interpret these results, but each research study is its own problem, and the interpretation can only be some guidelines generally. When you want to talk about your specific analysis and your particular context, then we need to get to those details. So we can talk about some, again, general principles, but interpreting results is something that you learn by doing. And finally, what do we need to do a sample size calculation? And this is a bigger, or one piece of planning a good study. And so I'll talk about sample size calculations in that context. We want to design studies that will answer the questions that we have, not just collect random data and see what we can see. So the sample size calculation is part of planning ahead to determine what you want to analyze. Much of statistics can be broken down into descriptive statistics, which is saying something about the sample of data that you have. And we talked a fair bit about that last time, making tables and graphs, just summarizing the cases in hand. But usually you want to use those data to say something about a larger group. And so then you need to infer whether those results are still true in a larger population. So perhaps you have a study within your hospital and you want to know, does it apply to cases that weren't from your hospital, either at another hospital or at some other point in time, or just some other department that perhaps you actually didn't get data for. And we'll talk quite a bit about inferential statistics today. Here's just a reminder that although we're going to spend today talking about inferential statistics and some statistical analyses, a lot of the problem with data analysis is getting the data in the right format, collecting it in the first place, and then formulating it so it can be used. And we talked a bit about that last time. And you spend a lot of time doing it, and it's a crucial piece of the analysis. If you try to do a statistical analysis, or if you hand data to a statistician to do a statistical analysis and the data are no good, there's no hope for the analysis that you produce. So although it's the groundwork and not the fancy stuff, it is very important. So as you think about what data you want to collect to answer your questions, make sure that you collect the right data as best you can. There are two main types of statistical inference, hypothesis tests and confidence intervals. Both of these are procedures that use data to answer questions about a larger population, or so-called parameters, numbers that describe a population. After we remind ourselves or learn what those things are, we'll talk about how we can interpret those results. So these are tools that can be used. They produce numbers, but what can we do with those things? And one thing that statistical inference can address is really just formulaic. Is this number less than 0.05, or does this confidence interval include 0, or something like that? So there's kind of a rote answer to say, what does this hypothesis test or confidence interval tell me? But then there's more to it than that. Can we trust the procedure that we've done? Are there other explanations for what we're seeing? And we'll talk about some of the issues that come up and that you need to investigate to make sure your answers are robust and accurate. And one of the best ways to make sure your results are robust and accurate is to design your study before you do your study. Think about what it is you're trying to answer, collect the right data, and do the right analysis. Planning is hard when you're doing your initial analyses or don't know all the details of a particular analysis, but trying to think about as much of this beforehand allows you to not have regrets when it's all over about how you wish you had done it. Let me remind you that I'm happy to answer questions during the talk, and I hope if something is unclear or you want further details on something, please speak up so that I can address it. So hypothesis tests are the backbone of most statistical analyses that are reported in medical journals. The most common number that you'll see is a p-value for some hypothesis test. And not every hypothesis test is stated explicitly, but anytime you see a p-value in a table or in text, there is a hypothesis test that's been conducted. And that may be one reason that hypothesis tests are problematic, is that they're very easy to compute. And so we tend to compute them for everything, even when there's not a particular test of interest. Often authors will include p-values in your table 1 to say, is there a relationship between one random variable and some other random variable? And it's like, we don't really even care about that analysis or that result. We really have some other question that we're going to address in tables 2, 3, and 4. But it's just the nature, let's put a p-value in here. But we don't really care about that test, or it might not even be valid. So try to stick to hypothesis tests for the hypotheses that you actually are interested in. One thing I'll talk about later is that p-values are probabilities. And if you give yourself lots of chances to do something, rare events will happen. So these unusual p-values will show up if we do lots and lots of tests. So let's keep to the tests that we're actually interested in. The confidence interval has some of those same problems because it is closely related to hypothesis testing. But I prefer confidence intervals when possible, because it gives me all the information, or almost all the information, of a hypothesis test. And on top of that, it also gives me an estimate of some effect size. How big is a difference of two means, or how big is a difference of two proportions or probabilities? Rather than just saying, we know the difference is not 0. That's kind of what the p-value is going to tell us. The confidence interval will give us an estimate of, well, how big is that average, or how big is that effect? And many journals now require confidence intervals for important effects that are being analyzed. And I think that's a step in the right direction. All right, so I've mentioned hypothesis testing a few times, and I think some of you have seen this, or maybe even done this. But this is not hypothesis testing, but it is a form of data analysis. But don't confuse this with hypothesis testing. First of all, let's find some existing data set. maybe your mentor has a data set from a study he's done, or a colleague. Maybe you have an interesting data set somewhere, and you say, let's just find what's there. And so you pick a couple variables and you compare them, and you compute some p-value, or you look at one variable in several different groups and compute a p-value. And then when you get around to a small p-value, which we'll see in a minute, is evidence of an effect of some kind, then you say, okay, I found something. What was it that I was testing? Let me state the research hypothesis and the null hypothesis that go with this p-value. And that's a way a lot of hypotheses are reported or discovered, but don't fool yourself into thinking that you've successfully tested a hypothesis. This is hypothesis generation. If you find an effect in your data by searching around for it without any real biologic or medical understanding of what's going on, then you're just essentially finding an interesting fact that should be tested with new data. And so we're going to talk about what the correct order of events is for hypothesis testing, but this is kind of the reverse order of what you want to do. Don't compute the p-values and then figure out what the hypotheses are. Figure out what the hypotheses are that you're interested in, and then go test that hypothesis. This approach does have merit. There's a reason to do this, but it's to find things worth testing in the future, or perhaps someone else did something like this, and now you're going to use their hypothesis and collect new data and see if this effect is real or not. This is the appropriate order of hypothesis testing. First, formulate a research hypothesis that you think would be an interesting effect to you or your patients or the research community. Collect some appropriate data to address that hypothesis. Compute a test statistic from your data. So somehow summarize your data in a way that you can state how big this effect is, or whether this effect is present or not. And then finally compute a p-value at the end. So rather than starting with many p-values and coming up with one hypothesis after a search, you want to do it the other way. You start with one research hypothesis and carry it through to a p-value. So here's an example of how this might work, how to form a statistical hypothesis. Ideally, there's an interesting question from your clinic background, from some case studies you've seen in somebody else's background. Maybe there's some basic science going on, and you want to see if this translates to work in animals or humans. Or if you want to say, look, I've seen this with one type of drug, maybe it happens with another type of drug as well, it's related. Just something that you have seen that you think would be important if true. And then you say, well, you know what, rather than just guessing that it's true or hoping that it's true, I'm going to go collect some data and see if I can show that it is true. So one paper I was asked to help on a year or two ago was a physician studying congenital ptosis, and their claim was that the septal fibrosis may tether the eyelid in the primary position and impact the outcome of the attempted surgical repair. And that only means a little bit to me now, and it didn't mean much. It meant less to me before I started on this. But we had to have a discussion about, okay, how can we address this claim that you have developed after treating patients with congenital total, why do you feel this? Can we show this is true? And so on. And so together we translated this idea into a statement about some actual variables that we could measure. In this case, we studied the levator function, something we could measure, and compare it within groups that have septal fibrosis and those that don't. An alternative might be if there weren't something we could measure, but only something we could categorize, such as success or failure. We might talk about the probability of success in one group versus the probability of success in the other group. So the objective or hypothesis that we came up with was to claim that the preoperative levator function, measured in millimeters, of patients with septal fibrosis is on average less than that of patients without septal fibrosis. And so here's a claim that is specific to a variable and a certain group of people, and we can collect data on. So we've taken it's a fairly clear clinical hypothesis, but we've turned it into a more clear statistical hypothesis about what we think is happening in these two groups. I do want to point out that this statement does not cover everything that's in the bullet point above, where it said this may impact the outcome of attempted surgical repair. Right now, we're just investigating the initial piece, our septal fibrosis and levator function related to each other. Whether these things actually affect the surgical outcome or not is a separate question, and one we did not attempt to answer with this hypothesis. Sometimes when developing a research hypothesis, you may have a large aim that you're looking for or want to, but you may have to tackle it in smaller steps. So based on that claim, based on that, we want to be a little bit more specific. Whether it's worth writing it down as a formula or not depends on who you are. Sometimes it makes it more clear what you're doing. Other times the notation gets in the way. But basically, the research hypothesis is that there is a relationship between levator function and septal fibrosis. In particular, the septal fibrosis on average is less than on average in the septus fibrosis group is less than that than the levator average in patients without septal fibrosis. And we can write that as an alternative hypothesis says that the mean, mu, in the septal fibrosis group is less than the mean in the without septal fibrosis group. And that's really what we want to say is true. The way we go about doing that, though, is to set up a straw man to knock down. We're gonna claim something else is true and show that really isn't a good hypothesis, and then hope that if we reject or don't like the null hypothesis, if it doesn't agree with the data well, then we can claim that the research hypothesis has been shown to be true. So once you've got your statement of effect, what do you think the relationship or effect is? You want to reverse that and say what's the statement of no effect or no relationship, and that's going to be your null hypothesis. The preoperative levator function of patients with septal fibrosis is on average the same as that of patients without septal fibrosis. So rather than claiming there's a difference, we're going to claim that they're equal. Are there any questions about how I got, well, about anything so far, but perhaps how I got from the research agenda to these specific hypotheses? Okay.
No questions as of now, sir. You may
Great.
proceed, sir.
Thank you for checking in. Okay, so once we had our hypotheses written down, we were able to determine what data we needed to collect, and so a resident was sent off to review medical records of people that met the inclusion-exclusion criteria, which I haven't laid out here, but basically are, what types of people are eligible for this type of surgery that we want to investigate the outcomes of eventually, and we want to measure whether they had septal fibrosis or not, and what was their levator function. So they found 30 patients, 41 eyes were eligible. I'm not actually going to, well, anyway, okay. So it turns out you could also, instead of saying just no septal fibrosis or with septal fibrosis, you could divide those with septal fibrosis into mild and severe categories. So that right away, I see there's another possible comparison that we might be interested in is, among those 34 with septal fibrosis, are the mild and severe different from each other? And this is often how research projects go. You have a primary hypothesis, and then you see that there are other interesting questions that you can answer with the data, and you can continue on with further analyses. We don't want to get too much into mission creep and get off target, but if there are related things to study, they're worth investigating. So of course, the first step is just to describe our sample. So we look at the 41 patients. There are 34 patients in one group and 7 in the other. The average levator function in the septal fibrosis group is 3.65. In the no septal fibrosis group, there are 7 patients whose average levator function is 9.57. So looking at this, it appears that there certainly could be an effect here. The hypothesis was that the septal fibrosis group was going to have a lower average than the without septal fibrosis group. And certainly in our sample, that appears to be the case. Of course, there's variability from person to person. Not everyone in the septal fibrosis group had 3.65 millimeters of septal fibrosis or of levator function. The standard deviation on the right is it indicates how much variation there was in each group. So the third step in my hypothesis testing outline was to take your data and your hypothesis and compute a so-called test statistic, test being for hypothesis test, and a statistic just basically meaning we can compute it from the data. In this case, we want to look at the difference between the two groups. So that's the difference in means between the two groups. So that's the difference between X bar SF and X bar without SF. This term happens to be 0. It usually is 0. The null hypothesis claimed that these two things are equal, and so that term just goes away. And then this piece in the bottom has a couple components. First of all, it involves the standard deviations of the two groups that I mentioned. There's some variability within each group, and it also involves the sample size. And if the sample size gets larger and larger and larger, this standard error here in the bottom will get smaller and smaller and smaller. And if this difference is not 0, then this test statistic gets larger and larger and larger. Test statistics are often near 0 when there's no effect, and then are either large positive or large negative when there is an effect. And so having a large sample size often makes it easier to get a large test statistic. Obviously, other things that come into play in the size of a test statistic, and how big is the difference between the two sample means, how much variability is there in observation of these data. We can take the numbers from the previous page or just the raw data and compute a test statistic. There's obvious commands for R and SAS on how to do this, and they'll all give you that the test statistic is minus 3.227. Another key feature of the test statistic is that we know how it behaves if the null hypothesis is true. If the null hypothesis is true, the null hypothesis being that the means in the population are equal, then this test statistic is actually this will probably be relatively small because the means are equal to each other. There's going to be some variability down here, but t is going to be around 0. We just need to find out if this is too far away from 0. And that's what this null distribution will tell us. I'll go back to that slide in just a minute, but the idea is this is the distribution that we expect if the null hypothesis is true. And we got something way out here in one end. Okay. So how do we work through this hypothesis testing? Recall from geometry or a previous stat class or something else, class on logic, you can prove something is true by something called proof by contradiction. And the way that works is that you assume something is true. You make some logical deductions from that. So after you assume something, you can derive other true statements from those truths. But if you do that long enough, you may arrive at a contradiction. That is, you've proven something to be true, which you know is actually not true. And so then you say, well, look, if everything I've done since the assumption is correct and logical, I must have assumed something wrong in the first place. And so you conclude your assumption is incorrect. And that's essentially the logic of hypothesis testing. We assume the null hypothesis is true. So we're going to assume that there's no effect, there's no difference in average levator function between these two groups. We're going to do some probability calculations. We can't do strict logical deductions. Things happen at random, and we need to account for that variability. So we make some probability calculations that say, if the null hypothesis is true, what's the chance of getting something like I got? What's the chance of getting something like a minus 3.2? If that probability is small, and small is almost uniformly defined as less than 0.05, if you get a rare event, then you say, well, look, maybe I observed a rare event. It happens. But perhaps an easier conclusion is that the hypothesis that I started from wasn't actually true. And so our option there is to reject the null hypothesis. And the way we've stated our question, there are only two things that can be true, either the null hypothesis or the research hypothesis. Well, if I've rejected one of them, then the other must be true. And that's really the goal. That's really what you're kind of hoping to have happen. When we started, the research hypothesis is the first thing we stated, and that's what we want to be true. And so the fact that we reject the null hypothesis is kind of a win. We've shown our effect. We can go write our paper. What is this p-value? I've kind of mentioned it. The graphic hopefully shows you that in our data, we actually observed a test statistic of minus 3.2. We also would be equally surprised or more surprised if it was further from the null hypothesis, further from 0, further from no difference. And so we look at the probability of getting something at least this large. this case, it happens to be 0.008. So 8 chances in 1,000, that's less than the 0.05. And so in this case, we would reject the null hypothesis and conclude that there is an effect. If p is less than 0.05, reject the null hypothesis, and you can write things in your paper like, we have found a statistically significant result or a statistically significant relationship. The way to think about it is that the data are inconsistent with the null hypothesis. If we assume something to be true, we wouldn't likely get data like this. P is 0.05 or greater than, we failed to reject the null hypothesis. We made some assumption, we did some calculations, and we got something that was reasonable, something that was somewhat likely to happen. This doesn't prove that the null hypothesis is true. It's just, it says the data are consistent with the null hypothesis. So we can't go saying, therefore the null hypothesis is true, therefore there is no effect. That's not what you get to do with a hypothesis test. A hypothesis test is just, okay, we thought there might be an effect, we didn't see it. It might be there. Then there are many reasons you might not find it. It might be a smaller effect than you were expecting to see. It could be that just the p-value is large by chance. It can be small by chance, it can be large by chance. But you don't have the data to determine that the null hypothesis can be rejected. This 0.05 is very arbitrary, and there's no reason to just report that a result is not significant or report that it was significant and not also give the p-value. It may be that somebody else wants to use a more lenient criterion. Maybe they're happy with p equals less than 0.1 would be a result worth working with. 1 in 10 error instead of 1 in 20. Or maybe they want to be more strict, 1 in 100. If you report the p-value, each reader can make their own judgment about whether this is a statistically significant result or not. One thing we don't immediately get from a hypothesis test is a statement of how big the effect is. We concluded that the effect is not 0, but we don't really know much about the size of the effect. How different are the two means? Obviously, in our sample, we can just compute that difference. I alluded to this earlier. We can compute the difference between septal fibrosis and without septal fibrosis. And we find that the difference in the two means is about 6 millimeters. And so we could write something about our sample that says the average levator function for patients with septal fibrosis is 6 millimeters less than the average levator function of patients without septal fibrosis. But that's just a statement about our 41 patients. And we really, we care about our patients, but we really want to make a statement about the next 41 patients and the 410 patients after that, and the patients elsewhere who are undergoing this procedure. And so just like there's variability in measurements, I mentioned those standard deviations in the table, 2.2 and 4.8, there's variation in our difference in two means. For these 41 patients, we happen to get minus 5.9, but we very easily could have gotten something else with a different 41 patients or some other collection of data. And so we want to say what we would expect are reasonable values for the true difference. So we have information on a sample. Can we say something about the true difference, mu SF minus mu WSF? And that's what a confidence interval will give us. We want to say not just minus 5.92 millimeters in our sample. We want to say, we want to give a range and say, we're pretty sure the truth is somewhere in this range. So a confidence interval is a procedure, just like a hypothesis test is a procedure. If you do hypothesis tests correctly, then when the null hypothesis is true, 5% of the time you'll incorrectly reject the null hypothesis. So there's an error rate there, and there's a similar error on the other side. Confidence intervals the same way. If you build lots of confidence intervals, 95% of the time your interval will contain the truth, and 5% of the time it won't. Of course, you don't know which 1 in 20 is the wrong one, but the idea is you've got a procedure, you know it works most of the time, and so you'll say things like, with 95% confidence, something is true. There's some formulas for this. In this particular situation, we're going to take the difference in the means in our sample, and then give ourselves a margin of error. We're going to subtract some constant, and this should look familiar. A lot of it is what's the denominator of the test statistic. We're going to take the difference in our sample, subtract a margin of error, take the difference in our sample and add that same margin of error, and say with 95% confidence, the true difference in levator functions averages is between this and that. With 95% confidence, the average levator function of patients with septal fibrosis is between 1.52 and 10.33 millimeters less than the average levator function of patients without septal fibrosis. So now, instead of talking about just the 41 people in our sample, we're now talking about all patients who are eligible for this type of surgery. And it lets us know that that estimate of -6, that 6 millimeter difference, we're really not that certain about it. We're certain that it's not 0. Notice 0 is not between 1.52 and 10.33, but we really don't have a good idea of whether this is 2 or 10. More likely it's around 6, but there's certainly lots of leeway in our estimate. So what can we do with a confidence interval and p-values? They're both related to statistical significance. P-values in some sense define statistical significance. If a p is less than 0.05, that is deemed statistically significant. In fact, that often shows up in people's methods sections when they're writing for a grant or a paper. They say p less than 0.05 is statistically significant. You can also get this from 95% confidence intervals when the confidence interval does not include some null value, for example, 0 in this case. That's equivalent to p being less than 0.05. So again, you can claim statistical significance. And all this is claiming is that some observed effect is not due to chance, or apparently not due to chance. That's the statistical part of the conclusion. The clinical part takes a little more effort, and the p-value of the hypothesis test we just conducted doesn't really tell us anything. It tells us whether this result was likely due to chance or not, or likely if the null hypothesis is true, but it doesn't tell us how big it is. The confidence interval, on the other hand, can say, look, we think the difference is between 1.5 and 10.3. Are those meaningful? Is a difference that large important to a clinician? And as a statistician, I often can only phrase this question to others to try to help them answer that question. I don't know if a difference that large in the levator function is important or not. I don't know what a good value is or a bad value is. And so that's where there's another discussion between the clinician and the statistician to say, look, we've shown that there is a clinically meaningful effect. Maybe when we had started, we were thinking anything larger than 1 millimeter difference would be important clinically. We showed that. Our confidence interval went from 1.5 to 10.3. On the other hand, maybe an important difference is 20 millimeters. Well, it's not that large. We know it's no bigger than 10.3. So we've made a clinical conclusion there as well. And then, of course, there's the chance that maybe 5 millimeters was clinically important for the difference of these two means. And we can't really decide at that point. There were certain values less than 5 millimeters and other values more than 5 millimeters within our interval. So we can't speak to whether it's clinically meaningful or not. So the statistician part, or the statistics part, is saying, are there real effects? That means not due to chance. Are the effects important? That's a clinical statement. That's a little bit different. Confidence intervals can help here. The interpretation piece is why might there be effects? Before I talk about why some effects might be observed, I want to take another 10-second break to see if there are any questions.
Sir, I had a question, sir.
Yes, please ask.
Sir, I just wanted to know what is the best method for hypothesis testing as of now, sir?
Okay, so the best method for hypothesis testing is specific to the problem at hand. In particular, what data do you have and what hypothesis are you trying to answer? So hypothesis testing is an idea. I've talked about it in general principles and then given an example for comparing two means. And what I've outlined here is the best method for comparing two means. If I had proportions, or if I had three groups or one group, then the implementation in that situation is different, but the general principles are the same. Figure out a research hypothesis that you want to show is true. Figure out the alternative, the null hypothesis that corresponds to that hypothesis, and then compute the appropriate test statistics. So those steps are pretty timeless. They're what essentially Fisher laid out 100 years ago. The actual implementation for different situations, whether it's groups or regression or whatever, that changes slightly as the data changes. But generally, I would say, the best method of hypothesis testing hasn't really changed.
Yeah, thank you, sir.
Thank you. So as we talk about why we might be seeing an effect, why are these two means different? There are several ideas that jump to mind. One is that there's a causal effect. The fact that two variables are related to each other is because one is causing the other to happen. In some sense, that'd be very nice to be able to claim and show, but often it's a high bar. You need special data collection often to be able to make that claim. Sometimes effects show up due to confounding, kind of a third variable that's associated with both the variables of interest. Often there's bias in a study, either how the data are collected or how the analysis was performed, that need to be considered and are ruled out. And then, of course, p less than 0.05 is ruling something out at the level of 1 in 20. So it could be that we're seeing an effect due to chance. And so it's something to keep in mind if you happen to be doing lots of hypothesis tests. Don't be surprised if you get a few small p-values just by chance, and then don't make too big of a deal about it. There are adjustments that you can make for numbers of tests, but generally the right approach is to keep the number of hypothesis tests small and just what you're interested in, and not going all over the place. So when we want to think about causation in the example that we've just gone through, one reason we might have seen the effect is that septal fibrosis causes a decrease in levator function. That's kind of the way it was laid out in the initial presentation by the researchers, is saying when this forms, then the levator function is worse. There's another way that this could happen. Poor levator function may cause septal fibrosis. I think that was ruled out when I mentioned that what if the relationship goes the other way. They said, no, biologically that doesn't make sense. And that's the kind of arguments we're looking for here, is we've seen a relationship, what could explain it? And the top one is something that they believe could be true, the second one is not. And again, that's not a statistical question so much as just knowledge of the content. Confounding is a large problem in observational studies. These subjects were collected from the medical record, and it could be that the effect that we're seeing between two variables is really because of a third variable. Septal fibrosis is more likely to occur in older patients, as is poor levator function. And so it may not be that septal fibrosis is causing a decrease in levator function. It may just be that as people age, both of these are more likely. Age is an easy thing to measure usually, and so it's actually something we could try controlling for in an analysis. But there could be other things that either we can't measure well. Maybe it has something to do with air quality where the person lives, or some genetic differences between groups. And either these are too expensive or too difficult, or we don't know to measure them. So those unmeasured confounding issues are always a possibility. And your goal when interpreting your results is try to figure out or hypothesize, maybe that's not the right word to use here, but to figure out what are possible limitations of what we've done. Bias is also a problem in statistical studies. This is not necessarily a conscious bias, but it could be that it's not really that the levator function is worse. It's just that the presence of fibrosis is somehow affecting our ability to measure it. Either the tool that we're using or whatever is unable to be used as well on patients with fibrosis than patients without. And that may cause a difference in the measurement that it really isn't measuring levator function properly. It may be that certain patients are selected to be in our study and others are not. And if that selection is related to both our variables, that can cause an effect to appear when there isn't really one. And of course, chance may be the source of the effect. Your goal when conducting these studies is to minimize the bias. I wanted to say eliminate the bias, but that's rarely possible. But your goal is to be the devil's advocate and just try to think of what could be causing effects. Because you don't want to kid yourself or kid the reader that you found an effect that really is just some artifact of how you collected the data or the analysis that you did. And there are lots of different types of bias that it can occur. There's some bias that can be eliminated by good statistical practice. I mentioned the controlling for age in our levator function and septus fibrosis analysis. One thing I want to warn against is a reporting bias that shows up. Suppose we had 20 different ways to measure levator function, and we did the analysis of all 20 of those variables and then just picked one of them, the one that had the small p-value, to report. That's a so-called reporting bias. If you report in your paper, you just did one test on using this one measure, the reader would not know that you really went through an extensive search to find this effect that may just be chance. This can happen consciously if your goal is to really go find where there's an effect. then your project is really more hypothesis generation again, rather than hypothesis testing. But this can also happen as an unconscious way. There are many choices that you make when doing an analysis, and they all may seem logical at the time, but if you look at how you got from where you started to the analysis you're presenting at the end, try to determine if you've got a strong reporting bias that needs to be commented on. All right, so the last piece I want to talk about is study design. Part of study design is how many samples do I need, how many observations do I need, and there's some quick rules of thumb that you can use to say, look, I'm looking for a large effect. How many people do I need? But beyond the most basic questions, this gets very problem specific, and it's probably better to talk with somebody who does this more frequently than you having to do it once every 6 months or a year or 5 years or whatever. It's just an unusual thing to need to do exactly. So except for the basic cases, it's probably best to talk with somebody who's got the appropriate software to do this. But there is a good reason to do it. First of all, it lines up a statistician who may be willing to work on the project with you. But you need to do a power sample size calculation. You need to clarify what exactly is your research question. You can't determine a sample size if you don't know what effect you're looking for. So it helps you specify what is your primary outcome variable. You'll need to identify what statistical procedures you're going to use, and you'll have to decide what type of an effect you expect to see. So answering these questions help you clarify what you're actually studying. You may say, oh, wow, I see I need to collect more data on this particular, or I need a more precise measurement of that, or whatever. But by having to think through what analysis you're going to do, it'll help you determine what data to collect. In our example, we were doing a 2-sample t-test. A common way to measure the size of an effect you're looking for is so-called Cohen's d, which asks how many standard deviations are you from equality. So before we even did the study, we could have said, look, I'm really interested in a 5 millimeter difference between these two means. And I think based on gut feeling or a few measurements that I've viewed that the standard deviation is about 10 or something like that. Now it turned out in our data in one group it was only, I think, 2.5, the other one it was 4 or something like that. So we got that one wrong. But if you knew what all these things were, you wouldn't have to do your analysis. So a lot of this is guesswork. But as I said, it has benefits. It helps you plan out your study. Sometimes you're just willing to say, look, we really don't know much about it. Let's look for a small effect or a medium effect or a large effect. And actually, the large effects are the ones that are easy to find. So if you want to look for a large effect, you're in good shape. Your sample size won't have to be very big. You can actually get away with a reasonable sample size. If you're looking to show that there's a small effect, that's really difficult. If there's only a small difference, the small difference in the average of Levator function between this group and that group, it's going to be hard to show that it's not zero. There will be a lot of variation that makes the detection difficult. Anyway, if you're willing to just start with generic pieces, if the field that you're interested in always says, you know what, use a medium effect size, and in some sense you get off the hook and you can just use that. And once you declare, I'm interested in a particular effect size, you can then figure out how big your sample size is. I much prefer the second approach where you decide what's a meaningful effect, what would I want to see, what would I expect to see, and how much variability is in their measurement. And then from that, I can compute the standardized mean, the standardized effect size, or the D. And then you can use a table or a computer program to say, okay, if my effect size is this big, how many people do I need in each of my two groups? So to look for a large effect size, ideally, I would have at least 26 patients in each group. I had 26 patients in one of the groups and not the other. So I may have been underpowered to detect a large effect in that example. But effect sizes are really something that you ask beforehand. Excuse me, not effect sizes. Power calculations and sample size calculations are something you do beforehand. And you can report that you did them and what the results were, but never go back after a study and say, what was my power? Those post hoc power calculations are not useful. Report a confidence interval instead. We can talk about that some other time. If we're doing a one sample t-test, the numbers are a little bit different. We haven't talked about that today, so I'll just mention another quick way to determine a sample size is based on a confidence interval instead of a hypothesis test that says how much variability are you willing to have in your answer. That t-test I showed you earlier was a difference of means plus or minus some standard error, excuse me, plus or minus some margin of error. How much variability am I willing to have in my confidence intervals? We're going through a lot of election polling in the United States right now. A lot of the election polls shoot for about 1,000 people in their polls, because then their margin of error on their estimates is about 3 percentage points. So they might say the difference in support between the two candidates is this versus that, margin of error equals 3%. That's a big study. You'd be probably more likely to have a smaller study, but then you have larger margins of errors on your confidence intervals. Any quick questions on sample size calculations before I wrap up with some conclusions?
No, sir, no questions from Pondicherry, sir.
Thank you. All right. Well, thank you for your patience. We started about 5 minutes late, and I'm 5 minutes over. My apologies.
No, sir, that's absolutely fine, sir.
Okay. So I'll wrap up with just a few statements about a few takeaway points. Statistical procedures help understand variability due to chance. So the hypothesis tests and confidence intervals are summarizing what variability can be explained just by the sampling process, the fact that we have a sample of people instead of all people in our study. In my opinion, confidence intervals are superior to p-values almost all the time. I try, whenever I report a p-value, I almost always report a confidence interval on my effect as well. And often I'll report a confidence interval without a p-value when I feel the p-value is unnecessary. But we have to keep in mind that these procedures are only measuring chance variation. There are other reasons that we might see an effect or not see an effect. Interpreting the results of the procedures requires obviously the understanding of statistics to know the effects of chance variation, but also you need to know the context. And that's where a researcher and a statistician can jointly figure out what the p-values and confidence intervals are telling us. Bias can enter a study in many places. It can enter in the data collection process. Who are we collecting data on? What data, how accurately are we collecting the data on them? If data collection is a survey, why are people not responding? When they do respond, are they lying or misremembering? All these things can affect how data are collected. Bias can creep in when doing a statistical analysis. I mentioned earlier, if you do many analyses and report only one of them, that reporting bias can lead to an effect that may not really be there. And of course, bias can enter in interpretation. You started this research project with something that you probably really want to be true, or you really think is true. And so when you're interpreting the data, that may be the only thing you see. You have to be careful in these situations. Think about people who would disagree with you. What would they say is causing the effect? And then investigate those if you can. Certainly put them in your limitations if you can't rule them out, but it may be that you've implemented some analysis or data collection routines that will rule out certain problems. One bias that often creeps into studies is people dropping out of a study. Well, if you've designed your data collection so it's easy to follow up with people and there's very little dropout, then you don't need to worry about that type of bias. That's part of the good design of the data collection and statistical analysis that can minimize bias. So good designs include definitions of your primary outcome and exposures. Ideally, you've done this ahead of time so that you're not kind of making it up as you go along. The more leeway you give yourself at the beginning, the more likely you are to perhaps get into a problem of reporting bias. A good statistical analysis plan will help. Just like you can kind of redefine variables to help yourself, you can choose many different statistical analyses. And if you're not careful, you can end up reporting only part of the story instead of the whole story. And a good design will include a sample size justification. Why did you collect as much data that you did, or why did you stop collecting data? Sample size calculations can help you in two ways, at least two ways. One of them is to say, look, I thought I was going to need to collect data on 1,000 people, but I really only need to do it on 100. That's a happy day. You save lots of time and energy on sample size because you realize you're going to get an answer with a small sample, that you'll get a number based on a small sample that will answer your research question. And the other thing it can do is it can say, you know what, I'm not even going to bother. It's clear that the sample size I need just isn't feasible. Either there's no way I can do 500 surgeries of this type in any meaningful time. There's no way I could, there just aren't that many people with a certain disease, whatever. So the sample size justification as part of your statistical analysis plan can help define whether the study is even worth conducting. Thank you all for your time. I hope this has been helpful. I'd be happy to stick around and answer any questions that come up.
Yeah, hello, sir. I have one question. I have a question regarding p-value.
Yes.
So when we make the tables, we enter the p-value. So if the p-value, if it comes to be exactly zero. So should we mention it as 0.000, or it should be less than 0.001 or something? The exact p-value should be entered, or
Right. So p-values can be exactly zero. P-values are often zero when you round them to several digits because the effect is so large that the chance that it happens is less than 1 in 1,000 or 10,000 or whatever. Personally, I like to, I would just write 0.000 or whatever, however many digits the journal wants. But I get a lot of complaints is a strong word, but many people say it's not exactly zero. It's like, well, it's not exactly 0.032 either, but that's the number we're putting in there because it's the closest number. Anyway, So many people prefer to change it to less than 0.001 or whatever the number of digits is that's appropriate for the journal. Often the journal will have a policy, and whatever you submit, they will change it to whatever they like. I don't think either of those approaches is wrong. One situation that arises sometimes if you're doing, say, large genetic studies where you're doing by design thousands or hundreds of thousands of hypothesis tests, then it matters whether it's 0.001 or 0.0011 or 0.00001. And so then people start using scientific notation, 10 to the minus 3, 10 to the minus 5, 10 to the minus 7. But that's a rather specialized situation where you need to do that. So that was a long answer. The short answer is you can use either. My preference is to just report it as 0 to the appropriate number of decimals. But the doctors I work with here, the physicians I work with here, almost always prefer a less than 0.00 something 1.
Okay, sir. Thank you, sir.
Thank you.
Thank you so much, sir, for taking the time and efforts. It was a really informative session, sir. And all of us present over here, I'm sure all of us got really benefited by this. Thank you, sir.
Thank you very much for having me.
Okay.
Thank you very much, Dr. Chris.
My pleasure. My pleasure. I hope the rest of the series goes well.
Yeah, today is the last class. Thank you. Thank
Okay.
you very much.
All right, great. Congratulations, you're done.
Thank you, sir.
Bye-bye.
Okay, bye.